I wanted to welcome everyone to this morning's session on what's new in Java security. My name is Brad Wetmore. I am not Sean Mullen, who was the original presenter of this talk. He unfortunately was called out of town for a family emergency and won't be able to make it. He sends his greetings and wishes he could be here, of course. So what we're going to do today is talk about the new security features in the JDK, or in Java security specifically. We're going to talk about the security features, the enhancements, some performance work, and so on. Sean was the original presenter or creator of the slides, and he will be presenting these in his Twitter account. So if you're on Twitter, you should probably see these soon. I don't know exactly when. It just depends on when he's able to get to it. His Twitter handle is Sean J. Mullen, and you can contact him then. I would also like to note that there is a BOF that's going to be presented by another member of our team, and that will be in Moscone room 309, which is just kind of down the hallway here to the right, your left, and then around the corner. And that's going to be at 10 o'clock this morning, and hope to see some of you there. The obligatory safe harbor statement, and then we'll just jump into the agenda here. So we'll start out with an introduction. We'll talk a little bit about some of the things that probably is familiar to all of you already. Then we'll go into the specific features that were added in JDK 10 through 13. We'll talk a little bit then about the cryptographic roadmap, which is a way that we can communicate our intentions of what the Java implementation from Oracle will be doing. We'll do a little bit of looking ahead at some longer term things that we're considering, and then kind of the obligatory conclusion here. So there were a lot of major features as well as some smaller ones, and so we'll be talking about pretty much all of those as well. So everyone has probably already seen the obligatory Java brick wall introduction to security. At the lowest layer, we've got the Java language and runtime security components. So these are the things that are already built into the language and into the runtime itself. For example, we've got all the access modifiers for packages, the private, the package private, and so on. There's also the automatic memory management and type safety, which makes your applications robust and secure. It also provides features that give you additional security at runtime, such as the bytecode verifier, which makes sure that all of your bytecodes are well formed. It also includes a security manager, which you can optionally enable at runtime, and it kind of acts as a central authority for making access control decisions to protect your sensitive resources from untrusted code. The next is the large set of APIs that we have. This has been developed over the last 20 years or so that allow you to build security into your applications. So we'll take a brief look at some of them. The JCE, the Java Cryptography extension, also known, or there's another version called the Java Cryptography architecture. And the names for those are actually historical, but essentially these are all your low-level crypto APIs. We have things for public key infrastructure, for JSSE, for TLS and SSL. We also have an API for SASL, which is a simple authentication and security layer. There's APIs for generating XML signatures, for smart card I/O, and then there's also one for authentication and authorization service, which is kind of cool. Most of these APIs are all provider-based, which means that the APIs are abstract, and there's implementations below it, what we call providers, that actually the calls from the top level are routed down into these individual providers. So that allows you to implement your own providers or add in a third-party provider that will do something that either we don't do or some replacement mechanism that, let's just say somebody's got a faster implementation of an algorithm. Finally, on the top layer, we do include a set of tools for managing security within the JDK. Keytool is the primary one. It manages key stores and their contents. There's a tool called jarsigner, which takes and signs and verifies jar files. There is another tool called policy tool, which is on its way out. So it really hasn't been a very successful tool, so we're just going to go ahead and take it out unless we start hearing some major outcries from it. And then there's also Klist, Kinit, and Ktab, which are Kerberos tools that aren't available natively on Windows implementation, so we provide these as part of our Windows distribution bundle. So those are some of the components just in a nutshell here. So anyone that works in computer security knows that the security landscape changes all the time. Our world, all the applications are much more connected than they've ever been before. So of course, security needs to be a critical piece of that. Security threats, risks, compromises, they're all real and need to be constantly dealt with. Now, over time, the cryptographic algorithms that you use today will be broken. Anybody remember DES? DES export, RC4. These are all algorithms that used to be, state of the art way back when, and unfortunately now they're just please don't use them. They're broken, and there's lots of research papers on those. New and security technologies will always emerge. We have post-quantum crypto. It's coming. So we just can't sit on our hands here. We've got to really keep updating the platform, add new algorithms, and continue to move the platform forward. So what are we doing? In the past 2 years, we have added support for many new cryptographic algorithms and protocols. We continue to strengthen the platform with a secure out-of-the-box configuration that protects you from the weak algorithms. So we talked about the cryptographic roadmap. Well, that'll play in a little bit here. We've also added some improvements to the tools to help detect security problems or security issues. And we've also added some security features and enhancements to improve the performance. So we'll see a little bit more of that in a bit. So let's take a closer look here on the security features and enhancements in JDKs 10 through 13. This is kind of the summary slide of what we've done in the last 2 years, and we've definitely not been sitting on our hands. JDK 10 was released in March of 2018, JDK 11 in September, JDK 12 March, JDK 13 September. So you kind of notice there's that 6-month cadence that has been talked about at length. So by doing so, we don't have to wait for the 3-year cycle like we used to have to do with JDK 8 and JDK 9. If you remember, JDK 9 took a long time to get the modularity right. So over the last couple years, we've had 4 major JEPs, and then we've also had a bunch of security enhancements that we didn't actually file JEPs for, but we're still worth discussing. And there was 81 of those. So these are things just kind of all over the place. So we'll talk about some of those in a little bit. So JDK 9, I know there's probably some people that are still using JDK 8, and it's great. It's it's pretty state of the art, but JDK 13 and especially 11 have a lot more things in them, and that all based itself off of JDK 9. So in JDK 9, we just to talk about it for just a little bit, there were a bunch of major features that went in here. We have DTLS, the datagram transport layer. We changed our key store default from JCEKS or JKS into PKCS 12. So anyone still using anyone using JKS still, please consider moving on to PKCS 12 as your default. And that is configurable using a system property, security property in the java.security file. We also improved the security application performance. There was a new TLS extension called ALPN, or Application Layer Protocol. There was a lot of work done on performance for instruction offloading, so we offload it to a chip instead of doing it all in software. OCSP stapling for TLS was another feature to kind of help improve the TLS performance. There's a standards-based DRBG, which is it's a deterministic random number generator that was added in 9 as well. SHA-3, and then we've also started some work on disabling SHA-1 certificates, and we'll talk about that more in a little bit as well. But this is not a talk about JDK 9. This is more talk of JDK 10 and so on. But if you are interested in some of these older technologies, go check out the previous Java 1 sessions or Code 1. I guess they were all still Java 1 at that point. The links are there available for you. And there's also, in our documentation, we have a section on what's new on JDK 9. So when Sean was preparing his presentation, he was trying to think about the best way to go over each of the enhancements that we've done. He considered going through each release in order, and then he decided that just didn't make a lot of sense because it's easier if things are grouped by functional area. So we're going to do it in that order. On each slide that follows, there's going to be a little icon in the upper right-hand side, and that will say which release the enhancement was delivered in. So with that, let's go ahead and take a look at some of the slides. The first one I wanted to talk about was a new algorithm called ChaCha20 and Poly1305. ChaCha20 is a relatively new stream cipher. It's a modern encryption algorithm that's resistant to side channel attacks. And it is also fast. It's faster than AES on systems without hardware acceleration. Intel and SPARC servers might have hardware native instructions that are available, but for things like phones and set-top boxes and all that, having something faster is obviously going to be better for us. So ChaCha20 is certainly getting more popular as things go on, and it's also one of the first replacement ciphers for RC4, because RC4 is pretty much should not be used anymore. ChaCha20 is also a replacement, an optional feature of TLS 1.3, which we'll talk about in a bit here. So the combination of ChaCha20 and an authenticator called Poly1305, when you put those together, it actually forms what we call an AEAD algorithm, authenticated encryption with associated data. So it's kind of like authenticating your data to make sure it hasn't changed in transit, kind of like the old Macs used to be. So let's see, I think I got the comments there, yes. So this was all defined in RFC-7539. If you're interested, please check out JEP 329, and the link is there for you. So within the JDK, how did we actually implement it? Well, there's a few new standard algorithm names. There's ChaCha20, and there's ChaCha20 Poly1305. So by itself, when you just say ChaCha20, you're going to get just the cipher. You're not going to get the authentication part of it as well. So when you're creating keys and so on, you just say, give me a key generator, get instance of ChaCha20. When you call the cipher, you want to get instance of either ChaCha20 or ChaCha20 Poly1305, depending on whether you want AED mode or not. There's also some parameters that need to get stuck in there as well, and so you would call algorithm parameters.getInstance ChaCha20 Poly1305. And now there's, depending on whether you're using ChaCha20 or 1305, there's a new API called ChaCha20 parameter spec, and that's available for use with just the ChaCha20 cipher. If you are going to use the AEAD mode, all you need is the IV parameter spec API. And that is done for backward compatibility. We hope eventually to get this backported into earlier releases like JDK 8 and so on. So we're trying to keep the number of API changes at a minimum for those folks. So JEP 329 has all that kind of information. And this was all done in JDK 11. Now, note this is just the cipher. This is not adding it to TLS. That was done later. Another one for key agreement is curves 25519 and curve 448. These are variations of elliptic curve algorithms that are much more efficient than the standard ones, the standard SECP 256R1 and so on. The curve 25519 gives you about 128 bits of security. 448 is about 224 bits of security. The nice thing about these is that they're faster and they are much more resistant to side channel attacks. And they're an optional feature, but we've went ahead and implemented them in JDK 13. We'll talk about that in a little bit here. These are all defined in RFC 7748, and of course, JEP 324 has all of the details. For the key agreement, this gets a little more difficult because we have some new APIs. The existing elliptic curve APIs are just not sufficient for what we needed to do. So we went ahead and created a few new APIs. We'll talk about those in just a second. The implementation itself is in pure Java. So there's no native code like we had to do with some of the other elliptic curves. There's a very efficient algorithm that was described in the RFC, and we followed that to the letter. It does outperform these other implementations of P256, 384, 521, and so on. The standard algorithm names for these are XDH, which the X is for the X25519. So it's an X Diffie-Hellman. And then there's also the algorithm name X448. And this is used in the key pair generator, key factory, key agreements, and so on. There is a new named parameter spec API for specifying parameters using just a name. We don't have to give it a lot of other options. So 25519, SECP256R1, and so on. So you can use a name parameter spec instead of just giving lots of parameters in a specific API. Getting back to the APIs for 25519, there is XEC key for X elliptic key, X elliptic key private key, XEC public key, and then the associated private key specs and public key specs. And again, these are all different and distinct from the current EC APIs. So if you're interested, please check out JEP 324 for more information about that. RSASSA-PSS. There is a mouthful. Sorry. RSASSA is a RSA signature scheme with appendix, and then it's a probabilistic signature scheme. It's defined in RFC 8017, also known as PKCS number 1 version 2.2. In previous releases, we've been supporting PKCS number 1 version 1.5. But the newer versions of the RSA signature scheme were lacking in some areas, and it needed to be more provable. So they went ahead and added a new version into it and came out with a new RFC for that, version 2.2. I mentioned it was based on a provable algorithm, and it's probabilistic rather than deterministic, excuse me. One of the things that you'll see in a minute is that this is actually a mandatory requirement of TLS 1.3, so this was nice to have in here. For the details of how to implement this or how to access it from Java, we have a new standard algorithm name. It's RSASSA-PSS. Sorry for the long name. To get at it, you would just use a key pair generator, get instance, RSASSA-PSS. And same thing with signatures. You just do a get instance with that horrible long name. There's new classes available. There is one for PSS parameter spec. And so what we do there is we take the message digest name, the message, excuse me, I forgot the MGF, mask generation function name. Then we pass in a parameter spec for any other options that are needed. There's a salt length and a trailer field, which is like an extra little byte that determines which variant you're using. There's some constructors that needed to be updated to support this PSS parameter spec. So you'll see things like RSA key pair generator spec. It takes an int key size, a big integer for the public exponent, and then this new PSS parameter spec called key params. There were similar constructors for all the different other variations. There's RSA private key spec, RSA public key spec, RSA private CRT key spec, etc. Next, the Sun PKCS 11 provider. We used to support version 2.2. That was quite a while ago, and there were a bunch of new algorithms that have been implemented in other providers. So these would be things like RSASSA-PSS, SHA-512, AES-GCM, and so on. And we weren't able to access those using the older version of 2.20. So the 2.40 was standardized a few years ago, and we went ahead and implemented access to some of those algorithms as well. And that was in JDK 13. Now getting to the TLS enhancements. I would say we've done a lot in the different releases, but the TLS enhancements in 1.3 are where we spent a lot of our time in JDK 11. TLS 1.3 is our RFC 8446, and it was a huge, huge overhaul of a protocol. It's been ongoing under development for years, and it has two main primary benefits. The first is that it enhances security. The second is that it improves the speed. By the security, I mean it removes the support for some of these outdated cryptography algorithms. Static RSA, once you get if the RSA key is ever broken, you can basically decrypt everything immediately. It also got rid of the older Diffie-Hellman key exchange in favor of the elliptic curve Diffie-Hellman key exchange. It got rid of some of the CBC or the cipher block chaining modes. The base for MD5 and SHA-1 is now gone. We got rid of triple DES, RC4, and so on. So all of these are now gone from the standard. That's caused some consternation in some circles, but for the people who are really concerned about the security, this has been a godsend. It also removes some of the unsafe features that have had problems historically, got rid of compression and renegotiation. It also requires some new modern algorithms. I mentioned RSASSA-PSS, and there's also ED-DSA, or Edwards curve DSA. Edwards curve is actually not required yet. It's an optional feature, but we're working on that as well. Cha-Cha-20 is another one, Poly 1305. There are cipher suites based on those algorithms. And there's also the 25519 X448 key agreement. So some of these came a little bit later. We didn't get everything into JDK 11. We just did as much as we could, and then we're adding things as we continue on. So in terms of the speed, we actually have a new handshake model in TLS 1.3 as well. It used to be you had a client, you had a server. The client would send a hello, the server would send a hello back with certificates, and then the client would do some computations, and it would send back a finished message along with some other stuff, and then the server would send back another finished message. So it was 2 complete round trips. So what they did in this case is they made it into just a single round trip. So the server or the client sends something over to the server along with some keys that it might use to negotiate, and then the server says, oh, okay, that works for me, we'll go ahead and do it, and now we're ready to do our communication encrypted. There's also another variant which is called zero round trip, where the client can basically just send a message and then start encrypting everything and sending it in the clear. That has proved a little bit problematic for our APIs. We're still talking about how we might want to consider implementing that, but for the time being, we're not doing zero RTT. So we have the new handshake model, fewer round trips, and there's faster algorithms that we can use as well. There we go. So for the Java details specifically, we have some new algorithm names. The first algorithm, of course, we're going to just continue on with our normal naming convention, where we have TLS v1.3. This is just continuing on from TLS v1.2, 1.1, and so on. The cipher suites, there's a bunch of new names. The IETF standardized on those names, and we're just going to go ahead and continue to use those names. So we have cipher suites like TLS under AES under 128 under GCM under SHA-256, and same thing for the 256 variants as well. There's new security properties for determining how long you can use a cipher or a connection before you need to re-exchange keys or do a key update. And that is a system property called, a security property, excuse me, a security property called jdk.tls.keylimits, and then you specify the name of the algorithm and what option it is, and then how much data you can exchange before you need to do that key update. You can either specify it as number of bytes or as a 2 to the power of something. So our current default is 2 to the 37, which is about 134 gigs. TLS 1.3 is enabled by default on both the client and the server sides. That's a change from when we did 1.1 and 1.2, when we ran into all kinds of problems back in JDK 7, where we ran into interoperability problems. But in 1.3, we went ahead and just made that the default in JDK 11. If you have any other questions about 1.3, see JEP 332 for more details. And there have been a few implementation bugs that we have been made aware of, and we're fixing those. Do see the release notes for the latest release to get a known list of compatibility issues. So I mentioned Cha-Cha-20 a little bit earlier, and 1305. It is available as a TLS cipher. We implemented the algorithm itself in JDK 11, but we didn't actually implement the cipher suite until JDK 12. So you'll need to be on 12 in order to get this. It has been added to the Sun JSSE provider. The cipher suite names is just the IETF name for the same thing. It's TLS Cha-Cha-20 under Poly 1305 under SHA-256. We did also implement Cha-Cha-20 based cipher suites on earlier versions of TLS. So if you want to be on TLS 1.2, you can do it as well. There's the names there. I won't read them because it would be taking way too long. And these ciphers are all available by default. X25519 and X448 Diffie-Hellman elliptic curve support. So again, we talked about that a little bit earlier, where the algorithm was available for the crypto part, but it wasn't available in TLS. Well, we added that in JDK 13, which just released a little bit ago. We have added support for these named groups in TLS, and it's in the Sun JSSC provider, of course. These curves are actually supported all the way back to TLS version 1. So 1.1, 1.2, 1.3, and 1, of course. So the default list of named groups is now 25519 as the most preferred. So hopefully browsers and such that are using that will be able to take advantage of that increased performance. Then we have SecP 256R1, 384, and so on. We've also got some finite field Diffie-Hellman algorithms, but they're kind of way at the back because the elliptic curves are much more performant. If you don't like that list, though, there is a system property called JDK TLS named groups. All you have to do is set that and then restart your JVM, and you can have your own preferred list. So again, all these are added in JDK 13. A few other notable TLS enhancements that you might be wanting to know about. We do have a stateless server session implementation that was added into JDK 13. What that does is when you have large servers and they are creating lots of connections, normally you want to put them in a cache. And somehow that cache can just grow very, very large unless you make other ways of coming up with ways to avoid that cache problem. You don't want to throw away your data. So the mechanism that was come up with is to do a stateless server. And what you do is you take all the information you need in the server side and encrypt it into a packet. You send that packet across. The client then stores it in its session. It's part of a key update. And then when the client wants to reconnect and do a new handshake, it just sends that bundle. The server looks at the bundle, decrypts it, and says, oh, I know exactly what to do with all these data bits here, and it doesn't have to do the full handshake. So it's kind of a nice optimization to avoid large data bits on servers. For this release, we're still getting some of the bugs out. There is a system property that turns it on. Currently, it's not on by default, but by just setting these system properties, you can play around with it. jdk.tls.client session, enable session ticket extension, and the same thing for the server. It is continuing to be enhanced in 13 and 14 and so on. We also changed the ordering of the cipher suites to improve the security. We moved the DHE-based security up higher so that you would have the property of forward security or forward secrecy. Some of the ones that are using SHA-1, of course, those need to be moved down a little bit lower, as well as suites that are using RSA key exchange. One other one that I wanted to mention about in JDK 13 is that the server-side cipher suite ordering is now the preferred ordering. It used to be the client would send its preferred order in the handshake message, and then the server would look at that list and use those as the basis for which came first. We did add a parameter a while back that said to prefer using it on the server side, so the server takes its list instead. But in JDK 13, we went ahead and just made that the default in our Java implementation. So jumping off of TLS now, moving on to XML signatures. The XML signature is just the APIs and implementations for generating and validating XML signatures. So there's one implementation detail to talk about here. We did update the implementation to Apache, and I apologize if I slaughter this name, Santuario? Santuario, I knew I was going to slaughter it. Version 2.1.3. This brings in support for several new algorithms defined in RFC 6931. It has some SHA-224 and SHA-3 digest algorithms. And it also includes the new RSASSA-PSS algorithms. And this has also been backported to Oracle JDK 1105 and 8U231. So if you're using that, you might appreciate those being available. For tool enhancements, we're going to talk a little bit about JDK 9 because we want to make sure you're aware of some of the enhancements that went into that release because it does have a little bit of effect on what happens in later releases. So in jarsigner, remember jarsigner is the thing that we use to sign jars so that they can be executed with privileges. We put in some weak algorithm and weak key size warnings. So this was all done in JDK 9. We backported this to 8U191 and 7U211. So let's look at this command line option here, jarsigner-keystore. We've got a digest algorithm of MD5, and we're going to use a signature algorithm of MD5 with RSA. So we're going to take that a.jar file that we're providing, and we're going to sign it with small key. All right, so type in the password, and the jar is now signed. But it also gives you a warning saying the MD5 algorithm is weak, and it's a security risk. Same with MD5 with RSA. It's a security risk. And the RSA signing key has a key size of 512, which is considered a security risk. So all those warnings should kind of give you a, hey, let's not do this. Try and use something else unless you have absolutely no choice. Also, when you verify the jar file, similar output, but there's actually a little bit more in that we will now treat that jar file as unsigned because it's been signed with a weak algorithm and is now disabled. So you might want to rerun jarsigner, and you can use the verbose option to get some more information about what you might do for it. If the jar file was signed here, yeah, so if you're doing the verbose option will tell you more about specifically what the problem is, and then it will also tell you why this is now considered a security problem. And the reason is because jdk.jar.disabled-algorithm at the very bottom there has these options that say not to accept these algorithms anymore. So MD2, MD5, small RSA keys, small DSA keys. So you will need to go update your security property if that turns to be a problem for you. We also did similar things in keytool when you're actually generating keys. So this was done in JDK 9. This was also backported to 8U151 and 7U171. If you're trying to generate a key pair using keytool, and you're using a RSA key alg with a signature algorithm of MD5, all right, it will say, I'm generating a key, and oh, by the way, MD5 with RSA is not a great idea and is considered a security risk. So you might want to rethink that. Same thing if you're trying to export things. The security certificate uses MD5 with RSA, so again, security risk. So these are all the warnings that you might be wanting to get. If you have multiple keys, it'll tell you which one has the problem. So if you have a certificate for B, certificate for C, and it will tell you, warning, B uses an MD5, warning, C uses 512 RSA. These are all problems. And then it also gives you another warning that says, JKS is a proprietary format. You might want to consider moving to PKCS 12. So one of the other options that we added to keytool, my personal feeling, I'm not crazy about where this dropped, but we ended up with it in keytool. And the keytool is to show info of TLS. So sometimes people want to know what protocols are enabled by default, what cipher suites are available by default. So if you do show info TLS, it'll actually tell you those things instead of having to write that 5-line program that I'm sure we've all written before. So it'll tell you TLS 1.3, 1.2, 1.1 is enabled by default, and then we have the enabled cipher suites. And the first 3 are TLS 1.3 only. The next ones are available for 1.2, and then we just don't have room on the slide for the 25 or 50 that are available. Also, for those of you that use Flight Recorder, we have a bunch of new security events for those now. There's 4 of them. The first one is jdk.security property modification. So this will tell you all about what properties were modified. Same thing for TLS handshake, for X25519 validations, and for certificates, specifically what the contents were of those certificates. Again, this was all added in JDK 13. What does that look like? And I apologize for the small font. Hopefully you can at least get an idea of where things are here. So on the far left side over here, you have the new types. And the one that we've highlighted here is TLS handshake. So now we can actually see that there was a peer host that was connecting to port 80 using TLS. Here's the cipher suites, the timing, and the certificate ID. And then you can do some searching based on specific criteria, and it's just a nice little way of adding a little bit more debugging to mission control, or to Java Flight Recorder, and then using mission control to understand what happened. Sometimes when you turn on the debugging, it's just too much information and it overwhelms it. So this is a little bit nicer. And turn that off. Okay, there we go. So that kind of finishes it for the main enhancements, but I did want to let all of you guys know about the cryptographic roadmap that we have. The cryptographic roadmap is Oracle specific, however, other implementations may choose to follow what we do. It is available at java.com/cryptoroadmap. It's really a heads up of what things are coming or what things have already happened that you might want to be aware of. So these would be changes to defaults, support for stronger algorithms and protocols, and so on. We realized that we needed a better mechanism than just putting it in some documentation somewhere. So it shows all the prior changes to date. In general, we do try to backport all of these disabled algorithms to previous releases with some exceptions, but it's usually the rule that we apply them to all the different releases. One thing to note is that it may or may not apply to other folks' releases. Some OpenJDK provider may decide, I really want to have RC4, so they'll take the RC4 out and include it in their release. So here is a quick snapshot of what that roadmap looks like. A lot of text up at the top, of course. And then we talk about the next things that are coming up. And for those of you who really like TLS 1.3, it's going to be available in JDK 8 soon. We're still working on a date sometime in 2020. So if you look at the date, or look at the titles of all the columns, we have a targeted date, targeted release, algorithm protocols that we're going to be changing, the action, and then how to disable or how to test and enable the change. So if there's something that we can do to kind of give folks a chance to test it out before it goes live, we can do that. And then the change log, of course, just talks about what we're doing. We also wanted to mention, this is a little bit lower down on the same page. The release changes, same columns, but there's the reverting instructions. So let's say that you went in and downloaded the latest version, and all of a sudden your RC4-based ciphers no longer work. How do I get around that? Or your Kerberos DES, or anonymous cipher suites, and so on. So you can go figure out how to change those back. This table shows some of the weak algorithms and protocols that we've disabled by default. Most of these were already announced in the crypto roadmap. This table shows the algorithm and the protocol that are weak and whether it's disabled in the different parts of the JDK. So MD2 should not be used in TLS, should not be used in certificate paths, sign jars, XML signatures, and so on. So the check mark means disabled. If it says NA, that means it doesn't apply. For example, there's no ciphers in like an RC4 cipher for a cert path. So those would all be NAs. So you can see the list of things we've done over the past several years. MD5, SHA-1. Now SHA-1 is a little bit different because we have disabled them for server certificates, but the root certificates, no, we'll be having those for a little bit longer. But we are still trying to figure out what our strategy is going to be on sign jars and for XML signatures, because so many people are still using those. We can't just turn it off yet. So we're still working on it. However, if you want to, you can go ahead and turn them off now. You just have to set the appropriate security property. Small keys and so on. Looking ahead. So we've got some future projects that we're looking at. The first one is the Edwards curve digital signature algorithm. And we have a JEP out for it, but we're still trying to figure out an API that's going to work. The X25519 kind of showed us that we could do it this way, but it adds a lot of APIs, and there may be a better way to do that. So we're still trying to get the best way to do this for EdDSA. It's JEP 339 if you want to look at that and participate in the mailing list discussion. There's also some certificate transparency. So this would be folks who want to look and make sure that the certificate that they just received was actually issued correctly and in a manner that's transparent. And then the last thing we're looking at is a next generation crypto API. These APIs that we're all familiar with, the Cypher, the Message Digest, and so on, they were all developed over the course of 20 years. And so we've got new design patterns that have come about, might be a better way of doing things. So we're looking, is it possible for us to come up with a better API that might be a little more flexible, might give you, an easier way of writing things than we currently have. So in conclusion, we have JDK 9 through 13 releases have a lot of new security features, lots of enhancements. The new 6-month cycle has really allowed us to deliver these things much more quickly. We don't have to wait 3 years to get TLS 1.3, or it just came out. They released the RFC in August, and we released our implementation in September, yeah. So we were actually able to get it out within a month. And then also, we're going to continue to strengthen and add security features to the platform. So keep tuned to this space for more, and we'll look forward to seeing you next year. One more bit of information for more information is if you're interested in the release notes, we have links here. There's also the JDK 12 and now 13 security docs and guides that are available. There is a security group within OpenJDK that we discuss all these implementation details as well as the APIs. We discuss that in our security dev mailing list. Twitter has Sean Mullen, who was supposed to be the presenter. He posts things from time to time. And then we're also going to be doing another BOF here in just about 10 minutes or so. And that's going to be talking about the future of Security Manager. Is it possible for us to modify it, get rid of it, or do we keep it? So just trying to figure out what's the best thing going forward. That will be at 10 o'clock, just about 20 minutes from now, just down the hall to your left, and then a little bit to the right, over by the bathrooms. And I think wasn't it Steve Jobs that always said there's one more thing? So yeah, we've got one more thing. We're hiring, actually, so if you're good, strong in cryptography, we would love to talk to you. And that is, I think, it for me today. So are there any questions? We got just a couple minutes. Yes?
We recently upgraded from Java 8 to Java 11 directly. In between, you notice there's a security policy 5-path cut change.
Yes.
I couldn't figure out which version actually was Java 9, Java 10.
So, okay, so the question was, he noticed that when he went from JDK 8 to JDK 11, that the location of the policy file or the security file had changed. Those actually had both changed. So as part of the modularity work that was done in JDK 9, there was a huge layout restructuring that was done. And there were now these configuration files. So we took all the configuration files and put them in a directory called conf. Okay? So under conf, there's another subdirectory called security. And then within security is the policy and java.security file. So that's where those both live. Yeah. So modularity is a little bit scary, but it's very nice to work in. And you can actually kind of get by using the compatibility mode of the module system. But if you haven't tried modules yet, it's actually pretty nice to work with. All right, well, if there are no other questions, I thank you for coming, and hope you enjoy the rest of your time at Code 1. I've been saying Java 1 for so long.